Welcome to Design End-to-End QoS Policies. In this skill, it's time to put on our designing hats, take what we learned in the last skill with QoS, and figure out how exactly we're going to design QoS into our networks. We're going to take a look at a few different mechanisms that we have at our disposal that Cisco wants us to know for the ENSLD exam, but also when we're doing our network designs, we need to consider things like congestion avoidance. And we're also, at the end of this skill, going to take a look at end-to-end QoS design frameworks. So what exactly do we need to consider when we're putting together our QoS policy? So come along and have some fun with me as we explore all of the different ways that we want to take QoS into account when it comes to doing our network designs. And with that, I will see you in the next video. When we're designing QoS into our networks, at some point we have to decide which mechanism we want to use for congestion management. And congestion management sounds a little bit fancy, but ultimately what it means is what type of queuing are we going to use? Because queuing is how we manage our congestion, hence congestion management. So in this video, we're going to take a look at some historical ways that we used to be able to queue our traffic, and then probably the more modern way that we want to deploy it into our networks today. Let's take a look. When we talk about our queuing options, I suppose we might as well get the first one out of the way, and that is to say that we have no queuing on an interface. We always have to have some level of queuing, but the idea of saying that we're not going to deploy a queuing architecture is to say that we're going to simply use first in, first out, meaning that we have a single queue on our interface, and the first packet that comes in to the interface is the first one that goes out. So the second packet that comes in is the second one to go out. This gives us absolutely no control over our environment. If it's one thing we've learned from our QoS conversations is that we want control over which packets are coming into our interface and which packets we want to drop potentially, or which packet should go first. So if we have 3 packets all lined up here in this queue, and this packet in the back is actually the most important packet to send, there's nothing we can do to move it to the front of the line using this methodology. And incidentally, by the way, this is the default behavior on every interface on a Cisco device. Now next we need to talk about a couple of legacy options that we're not going to use in our modern networks, but Cisco still wants us to know for the purposes of their exams, including the ENSLD. So first up is custom queuing, otherwise known as CQ. Custom queuing is an interesting name because even though it's called custom queuing, there's not a lot of customization we can do here. This is a technique that was developed by Cisco, and what's interesting is that we have 16 different queues in this method, and each of those queues is first in, first out. But these queues are not queues that we can send traffic to specifically. All we can do is define the size that we want each of these queues to be. So we start by putting all of our traffic into the first queue, and once its size has been reached, it will start placing traffic into the second queue. And then once that traffic size has been reached, the size that we've configured, then we start placing traffic into the third queue, and so on and so forth. This gives us very limited control over where our traffic is going. I would argue it really doesn't give us any control whatsoever. But it was an early attempt to improve the methodology around congestion management on our interfaces. Now next up is a fun methodology. It's called priority queuing, otherwise known as PQ. With priority queuing, we get 4 different queues, and they are tiered. Now tiered is kind of an interesting word. What we're saying here is that when we compare our 4 different queues, we're going to order them from highest priority to lowest priority. So we have a high priority queue, we have a medium priority queue, we have a normal priority queue, and then we have a low priority queue. And these queues will be serviced in the order of their priority. So as packets come in, let's just fill this, this drawing up with a bunch of packets here. And now we've got a bunch of packets. Well, we are going to take all of the packets out of the highest tiered queue first. And then once the high priority queue has been emptied out, then we can start servicing the medium priority queue. And at that point, once it's been emptied out, then we can start servicing the normal priority queue. But the problem at this point is once we get to normal queue, well, what happens if a packet shows up in the high priority queue again? Well, now we need to bounce back up to the high priority queue and get that packet out of there because it has absolute strict priority over that low priority queue that's hanging out at the bottom. And as you can imagine, during this time, the low priority queue is getting bigger and bigger with more and more packets getting inserted into it. This makes it so the high priority queue is going to be very, very happy all of the time, and the low priority queue, not so much. And unfortunately for us in our networks, low priority traffic is still usually important on some level. And so we risk this concept of starvation. Starvation means that we are not actually servicing a queue at all. So that queue gets starved for attention, meaning that it's going to simply start dropping packets like crazy once that queue is full. So these 2 legacy options should never be deployed into our modern networks. Today we have much better options, starting with, by the way, weighted fair queuing, or WFQ. Now, weighted fair queuing is probably not going to be our go-to queuing methodology, but we will see in a moment that we do use it as part of some other methodologies. So we do need to understand this. Weighted fair queuing is based on flows. We are going to assign a flow when it shows up on the interface for the first time. We're going to assign it into a new queue. That means we're going to spin up a lot of queues. Every time a new flow shows up on the interface, hey, new queue. And I know what you're thinking. Jeff, wait a second here. We've got thousands of network traffic flows on our network at a time. That could mean we have thousands of different queues on an interface. And you are absolutely correct. Cisco will support up to 4,096 different weighted fair queues based on our traffic flows. These are automatically created. Again, when a flow shows up, it gets assigned into a new queue. But because they're automatically created, we don't get a whole lot of control over this. So we're not able to say, hey, this type of traffic should go into this queue, this type of traffic should go into that queue. But weighted fair queuing does give us an advantage over these other options in that it assigns these flow queues into either low bandwidth or high bandwidth categories. The low bandwidth category is going to have things like voice over IP. And as such, Cisco is going to give priority to low bandwidth flows. So it does give a little bit of weight to more maybe mission critical traffic than we would get out of any of these other options, but we're still lacking some of the control elements that we would really desire to see in our networks today. So what would we deploy into our networks? Well, we should probably start by looking at class-based weighted fair queuing. This is going to sound a little bit familiar. We just talked about weighted fair queuing, but now it's class-based. So what's going on here? Well, what's happening is that we get to actually decide the queues. We're going to configure up to 256 different queues on a single interface using CBWFQ. And the coolest part about this is that we actually now get to classify our traffic. We've spent time in the ENSLD blueprint talking about traffic classification, but up until now we haven't actually gotten to classify any of our traffic. So we can classify the traffic, decide which traffic types go into which queues. We can set the length of the queues. We can make it so some queues, maybe they're not as important as others, and we want to give more buffer space to one queue over another, so we have customization over that. And very importantly, we can control how much bandwidth is guaranteed on a per queue basis. So let's draw this out here. Let's say we've got 4 different queues, and we start by classifying this. How are we classifying it? Well, when a packet shows up on an interface, we're going to take a look at the traffic tag. Maybe that's a DSCP tag, maybe it's IP precedence or class of service. But we look at that tag, or we use an access control list. The access control list might say all traffic coming from a certain host or a certain subnet should be placed into the appropriate queue. And so we're going to use this to assign our packets to these different queues. Furthermore, as part of creating these queues, we have now assigned bandwidth to each one. So we could say 10% bandwidth to the top queue, and we'll just go straight down the list here. 20%, 30%, and 40% of the bandwidth on the interface has been assigned to each one of these queues respectively. Now we introduce the concept of the scheduler. The scheduler's job is to decide which queue to service at any given time. Technically, there are schedulers with all of the techniques that we've talked about, but here is where the scheduler gets really important, because we're going to look at all of these queues servicing packets in them, but making sure that they abide by their guaranteed percentages. Meaning that if we are fully congested, I don't give Q2 more than 20% of the bandwidth, because that would rob the other queues of their respective bandwidth. But that said, let's say Q2 is pretty empty. At this point, we can share the bandwidth with other queues. So while the bandwidth is a guarantee, it doesn't mean that it's also reserved for that queue. Now, as I've drawn it out here, and as we probably imagine it, most of these queues are going to be first in, first out. That was what we'd expect. The first packet in is going to be the first one out. However, for the default queue, we can actually assign weighted fair queuing. It's not required, but it is an option that we have available to us. That means that all of the traffic that isn't placed into one of the other queues can be assigned a separate queue within that queue based on its traffic flow. So in a very real way, we have queues inside of another queue, which is something we can do with Cisco QoS. Now, this is a great system, and absolutely this is something we're going to want to deploy into our networks, but it's still missing something. Right now, as it stands, we are lacking the option to make one of these queues a priority queue. With voice over IP traffic showing up and a packet maybe arrives, we might want to send that out first. It's great that we're guaranteeing bandwidth, but the order of sending packets matters. And without the ability to prioritize traffic, we can't change the order in sending high priority packets out before low priority packets. Well, fortunately, we do have a modification to class-based weighted fair queuing, and that is called low latency queuing, or LLQ. Low latency queuing is taking class-based weighted fair queuing, so everything we've learned is still perfectly valid, and we're adding a strict priority queue. A strict priority queue will always be serviced first if there's any packets in there. However, low latency queuing comes with a caveat. and that is that it is still bandwidth limited. This is great news because we don't want to introduce that starvation concept into class-based weighted fair queuing. Now the way this works is we're going to assign the status of low latency queue, or in other words a priority queue, to one of these queues that are in our class-based weighted fair queuing deployment. So let's say Q1 is now labeled as the low latency queue. The low latency queue now actually has priority over the rest, so long as it's abiding by its bandwidth guarantee. Meaning that if it tries to exceed 10% of the interface bandwidth, we're still going to cut that off and say, okay, you've had your fair share of the bandwidth, and now we're going to service the other queues. But from a strict priority perspective, if our scheduler here is servicing Q3 and a packet shows up that's voice over IP or what have you in the low latency queue, we're going to stop servicing Q3, service the low latency queue, and then get back to Q3 once Q1 has been emptied out. This is how we reorder the delivery, the sending of packets. And it's absolutely essential, especially when it comes to traffic such as voice over IP. So in networks today, we absolutely want to configure low latency queuing, and we want voice over IP traffic to go into the low latency queue. Now let's wrap this up by talking about how we configure all of this. How do we bring it all to life? And Cisco has an interesting set of parameters and configuration sets that they call Modular QoS CLI, or MQC. What in the world is going on with this? Well, the idea here is that we want to use building blocks to be able to say, hey, how I identify traffic on one interface, I'd like to identify that traffic the same way on a different interface. And so the way we do this is we create something called a class map. Class maps are going to allow us to classify traffic. So basically we use the match command a lot. We say, hey, we're going to match this tag and place it into a particular queue. Next, we use a policy map. The policy map is going to apply, you guessed it, policies to the individual queues that we've defined in the class map. So some of our policies might be bandwidth reservations. And this is where we would assign a queue the low latency queue status. And lastly, we want to assign a policy map to an interface. And the way we do that is with a command called service policy. So this will work for deploying a policy to a single interface or to multiple interfaces. We can take one policy map and deploy it to multiple interfaces using service policy. Likewise, we could take the class maps and use them to form different policies. So maybe form a lot of different policy maps that get assigned to different interfaces. So different interfaces now can have different policies while using the same queuing classification. MQC delivers the ability for us to quickly and efficiently configure our QoS policy and deploy it across our network. So here are takeaways from this conversation. First of all, we need to know what all of our options are, including those legacy options. So we need to understand how custom queuing and priority queuing works and weighted fair queuing. But then we look really at class-based weighted fair queuing is what we're going to deploy into our networks. Class-based weighted fair queuing gives us control over classification and bandwidth assignment. But then, in order to get the priority level of treatment that we want, we're going to deploy low latency queuing. So LLQ is going to add a strict priority queue to class-based weighted fair queuing. And that's absolutely always what we're going to want to deploy into our network, especially if we have voice over IP running. And lastly, Modular QoS CLI, or MQC, that's the set of commands that we're going to use to deploy this into our environment. I hope this has been informative for you, and I'd like to thank you for viewing. We studied congestion management, now it's time to study congestion avoidance. Congestion avoidance is our way of avoiding congestion in the first place. Now, that said, we can expect that there's going to be some amount of congestion, that's why we have the queues. But what happens when those queues get full? So we have congestion on top of congestion. What are we going to do with these new packets that show up on our interface when we just got no room for those packets? In this video, we'll take a look at all of the different options that we have available to us from a congestion avoidance perspective. Let's dive in. We have a problem that we need to discuss. Let's say that we have a queue, and that queue only has so much space. So here's our queue. We're starting to put packets into this queue. Hey, maybe we even have a couple of queues here, maybe 2 queues or 3 queues. And so we've got packets that are showing up. We're classifying those packets, putting them into their respective queues. And then all of a sudden, one of these queues gets completely full. Well, unfortunately, the rest of the network keeps functioning, and so we've got a packet that arrives, and it's supposed to go into that queue, but again, we have no space for it. What are we supposed to do with this packet? Well, unfortunately, we have no choice but to drop that packet. If we have nowhere to put it, then away it goes. And we call this situation tail drop, because we're dropping packets that are at the tail end of the queue. So again, packet comes in. If we're full, then, well, we have no choice but to drop that packet. That's ultimately what we're talking about when it comes to tail drop. And there are 2 primary issues we need to understand with this. First of all, once again, if you've noticed a theme with QoS, it's this idea of control. We want to deliver as much control as possible to us as the network engineers for deciding which traffic to drop. And unfortunately, this gets rid of that control from us. For example, was that packet an AF11 packet, AF12, maybe AF13? We recall that we've talked about these DSCP per hop behaviors such as assured forwarding. And when it comes to assured forwarding, we might be putting all of the AF1 packets, whether that's 11, 12, or 13, into one queue. But this second number is supposed to indicate whether we drop it very often or not. In other words, we're supposed to drop AF13 more often than AF11. That's what that number indicates. The higher the number in the second slot, then the more likely we are to drop that packet. But this packet could have been an AF11, or it could have been a 13, or it could have been a 12, and either way, we never even got to look at it because we had no room for it. So lack of control is the first big problem. But the second big problem is an interesting one, because we call this TCP global synchronization. What in the world is TCP global synchronization, besides being a mouthful, of course? Well, what we're talking about here is the idea that as we fill up our queues, what we're going to find is that we are dropping absolutely no traffic for an extended time. While that queue is filling up, hey, life is good, right? We're not dropping anything. But then that queue fills up, network traffic continues to pile up behind it, and we spike, and we drop all kinds of traffic for a little while. But then that queue empties out again, law of averages and all of that. And so, hey, we're back to normal. We're not dropping anything. But then guess what? That happens again. And we spike up and we drop a bunch of traffic. And then we drop no traffic. And then we spike and we drop a bunch of traffic. And the characteristic of our network is that we go from periods of absolutely no drops to periods of a ton of drops. This has a weird effect on TCP, because TCP adjusts its windows based on what exactly is happening in the network and how much congestion there is, and specifically how many dropped packets there are. And so what we see out of TCP is that we ramp up our window sizes here, and then all of a sudden we hit all of that dropped traffic, and so we have to back off on our window sizes. And then we start to ramp up our window sizes again, and then we drop them off. And then we start to ramp them up again, and we drop them off. And these two situations basically continue to perpetuate because our queues empty out when our windows shrink. Because we've shrunk our windows here, we no longer are sending as much traffic, and so that allows our queues to empty out. But we get stuck in a loop, where as our window sizes increase, now we're back up here, and hey, our queues are filled up again, and we're just going to start dropping traffic. And our TCP windows never hit any kind of steady state operation. So we've got some problems to solve. As you can imagine, we've got some solutions that will help us with this scenario. Let's talk about those. The first of which is called Random Early Detect, or RED. Random Early Detect's goal is to smooth out this loss. We want to smooth it out because of all the reasons we just talked about. These spikes are bad for our network. So we're going to smooth out the loss, and the way we're going to accomplish that is by more or less saying, hey, every time a packet comes in, there's going to be a % chance that we are going to drop that packet. And I know what you're thinking. Wait a second, Jeff, we're going to have a % chance of dropping every single packet that comes into our interface? And generally speaking, yes, that is what I'm saying. When a packet shows up, even if the queue is empty, let's say a packet shows up in this second queue here on the left, we've got space for that packet, but we're going to run a check on it, and hey, there's going to be a % chance that we will simply drop that packet. Why are we doing this? Because we want to take this behavior of saying that we go from periods of no drops at all to tremendous drops in the network, and we want to average it out and say, you know what, we're going to have to drop some amount of traffic in our networks. What's packet switch networking? This is what we've come to expect. Our networks are built around this concept of packets being dropped. It's just our reality. So rather than trying to pretend like, you know, life is good, let's just not drop anything while we can, it causes problems. And so instead, we're going to average this out and smooth it out and say, over time, we are going to take some amount of loss. But the idea here is that we keep that loss consistent over time. Now, all that said, there's no real reason for us to drop traffic if life is really, really good. And so we're going to base this percentage on the size of the queue, or how full the queue is. In other words, the more full the queue is, the greater the percentage that we're going to drop traffic. And conversely, the less full our queue is, the less likely we are to drop that packet. And the goal of RED is to make sure that we never fill up our queues. The last thing we want is to rely on tail drop. And unfortunately, at the end of the day, if our queue fills up, even with RED in place, tail drop is still going to occur. Because again, what else are we going to do? When the queue is full, we have to drop the packet. So with RED in place, we have smoothed out our loss, and we can officially check TCP global synchronization off of our list of concerns. Because as long as our loss is averaged out over time, we don't need to worry about this synchronization concept. However, we do still have a problem we haven't addressed, and that is this control element. because every packet that comes in has a % chance of getting dropped. And we talked about these AF values, AF11 and AF12 and AF13. And in our scenario here with Q2, if that packet showed up and it was AF11, let's say, we're not supposed to drop that traffic. At least not before we drop an AF13 packet. But the problem is whether it's AF11 or AF13, either way we apply the same percentage to those two values. So fortunately we do have a modification to red that's going to fix this. And for better or worse, sometimes we still pronounce it red. But the acronym is different. It is weighted random early detect. Weighted random early detect adds a very key word here, and that is weighted. We are going to pay attention to the weight or the tag, the classification of that packet. Here's how this functionally looks. Let's say we have a queue, and we are starting to fill this queue up with packets. At some point, we want to trigger the threshold to start dropping packets for, specifically, AF13. AF13 is the, according to our scenario here, it's the packet tag that we want to drop first. And so there's going to be a % chance that we drop it, and that's going to grow over time until the queue maxes out, at which point, of course, it's a 100% chance of it getting dropped because it's tail drop. So as packets come in, if a packet comes in at this point and it's AF13, there's a % chance that it's getting dropped. But there's still a 0% chance that if it's AF12 or AF11 that it is getting dropped. So now we set a new threshold. Now we set the AF12 threshold. AF12 has a % chance of getting dropped starting here. And so now with this packet arriving, if that's AF12, we'll have a small % chance of dropping that packet. But we still have a 0% chance of dropping AF11. As we continue to fill up this queue with more and more packets, eventually we are going to have an AF11 threshold. At this point, we will have a small % chance of dropping AF11, but it ramps up a little bit quicker because we have less room to ramp up. But the point is, of course, as a packet comes in here, if it's AF13, well, AF13, there's probably a pretty good chance, maybe even a 70% chance that we're going to drop that packet. If it's an AF12 packet, then there's maybe roughly a 50% chance that we'll drop it. But if it's AF11 right on the threshold, there might only be a 5% chance that we're going to drop that packet. This is how we favor AF11 over AF13. And we can apply this to any tag, any type of tag that we're putting onto this queue. We want to build these thresholds such that we choose which tags to favor and which tags not to favor quite as much. But as you can imagine, with this scenario, we get that control that we are so desperate to have over the packets in our infrastructure. We want to have absolute control over which packets get dropped, at least relative to one another. And with weighted random early detect, not only do we get the problem solved with TCP global synchronization, but it delivers that control to us that we need as well. So as we look at this, if we rely on the default behavior of tail drop, we're going to have problems. We're going to lack control over which packets are getting dropped, and we have to deal with this TCP global synchronization issue. Fortunately, we have two different options available to us from a congestion avoidance perspective. First is simply random early detect, or RED, and that solves the TCP synchronization issue by smoothing out our loss. Basically, every time a packet shows up on an interface, there's a % chance that we're simply going to drop it. That's the early part of random early detect. However, we also have the other RED with the W in front, maybe a silent W, weighted random early detect. This is what we're going to want to configure in our networks. There's no disadvantage to deploying weighted RED other than potentially that we have to sit down and decide what the policy is going to be, and we have to configure. It does take more effort on our part. But weighted random early detect is going to assign that drop probability based on the different classes that we're throwing into that queue. And so it gives us more control over which packets are getting dropped. We can make sure, as we saw in our example, that AF11 traffic, for example, is never dropped relative to AF13 until that queue is almost full, at which point we simply do have to start dropping any kind of traffic that comes in. I hope this has been informative for you, and I'd like to thank you for viewing. We have two conversations that we need to have that are very related to one another. In the QoS world, these two mechanisms are known as policing and shaping. If we're not going to police, then we don't need to shape in most cases. But at the same time, we need to understand how both of these operations function. So in this video, let's take a look at QoS and shaping, and when and why we might want to deploy that into our network. Let's take a look. Let's take a look at a scenario where we have two routers connected to one another, and maybe this is upstream to some kind of service provider, where we have a service level agreement established between the two parties. So let's say this is supposed to be a 10 meg circuit. Now, what if this connection is using 10 meg Ethernet? So it's 10 meg down here, we've got a 10 meg SLA. At this point, life is good because the most traffic I can send meets that SLA. But what if this is a 100 meg connection or 1,000 meg? What if it's a gig Ethernet connection? how do I make sure that I'm abiding by that 10 meg SLA? And the answer to this is policing. We can use traffic policing to drop any traffic that exceeds our SLA. It effectively forms a barrier, so to speak, where if we exceed the bandwidth that we've all agreed that I will abide by this, well then, hey, we're going to start dropping that traffic. Makes sense, right? I mean, what else are we going to do with that traffic when you've exceeded that which we've agreed upon? This is primarily going to be an ingress concept. For the most part, we're not going to police our own traffic that we're sending out. Instead, policing is usually used to enforce an agreement from downstream customers or downstream organizations. But here's the problem with this concept. We've already talked about 10 meg and 100 meg and 1,000 meg as if it's a hard value, as if it's a number that we have, like a number of packets, for example. But the reality is that when we talk about bandwidth, bandwidth is this concept of traffic over time, or specifically bits over time. We have the same problem with bandwidth that we do with speed. When I'm driving down the highway, I'm going so many miles per hour or maybe kilometers per hour. But in either way, my speed at any moment in time is going to have to be averaged out over the last time interval, whatever that interval is. So if I look at the amount of bits per time, I might have sent a lot of different bits over a particular time interval. But if I'm going to call this 6 megabits per second, well, that would be some kind of average over a particular time interval. So the question in all this is, how do I actually police based on bandwidth? And furthermore, what about bursts? Is it fair for me if my customer downstream has been sending at 2 or 3 meg for a long time, and then all of a sudden, across a few intervals, I burst up to 11 or 12 meg and then immediately fall back down? Is it fair for me to cut that traffic off? I mean, technically by the SLA, yeah, I mean, it is perfectly fair that I could. Even though, if we average it out over time, they spent way less than 10 megabits per second. So we need a methodology to deal with both of these concepts, and the methodology we're going to use is known as the token bucket. Now, if you've studied QoS and you hear the phrase token buckets, you might already be regressing into some kind of nervous or anxious state. But I'm going to tell you right now, token buckets are not that difficult if we just unpack it in a way that makes sense. Because again, we first of all have to understand we're trying to solve this problem of analyzing how much bandwidth we're using over time. And we want to do this fairly, right? I mean, we've all agreed to a particular service level agreement, and maybe part of that service level agreement has said that the customer can burst. And so we need a fair way of dropping traffic when they've actually exceeded that SLA. So the way we're going to do this is we'll just draw this out as if it is a bucket, and we're going to put tokens in this bucket. Now, each one of these tokens, I tell you what, when I think of token, I think back to like going to arcades when I was young. And I'd go up and I'd put my dollar into the machine and I'd get 4 or 5 tokens out, and I could put those tokens into the arcade machines to play a video game. Well, that same concept is going to apply here. Every time I receive a packet, I'm going to look at the size of that packet. And based on that size, I'm going to pull out the appropriate number of tokens. Usually, each token is equal to 1 bit. So if I just received a 15 byte packet, well, that's 12,000 bits, and so that's going to be 12,000 tokens that I need to pull out. So I'm pulling tokens out as I receive packets, but meanwhile, I'm going to be filling this bucket back up with tokens. I'm going to be replenishing those tokens at a particular rate, and that is known as the committed information rate. This is essentially what the SLA says. In our earlier example, we said that our SLA was 10 megabits per second. So in this model, I would be refilling this with, roughly 10 million tokens per second. So now I have a straightforward way of determining whether my customer has actually violated the agreement that we've set into place. If I receive a packet and I have no tokens left in order to pull out of that bucket, well then at that point I'm going to drop that packet. And really this solves both of our problems, because now I don't need to worry about the fact that this is averaged out over an interval. This methodology makes it extremely straightforward as to whether I need to worry about dropping this traffic. Furthermore though, I don't need to worry about this burst concept anymore, because I can simply allow this bucket to hold additional tokens. And those additional tokens will essentially be used in the situation where my traffic bursts up. So maybe my SLA is again 10 meg, but I burst up to 12 meg for a very brief time. Well, if there's enough tokens in the bucket, then hey, we're good. And I can successfully send all of those packets, and those will be received and not dropped. Now this token bucket methodology is pretty straightforward, but it does get more complicated. Fortunately, within the realm of ENSLD, we don't need to worry too much about it. But be aware of 2 concepts. First of all, we have the concept of rate. We can have single rate or 2 rate policers, and we can have 2 color or 3 color policers. Ultimately, what this allows us to do is to categorize our traffic a little more granularly than either you made it or you didn't. So specifically, we can have conforming traffic, Conforming traffic in the policing world means that, hey, congratulations, you had a token available, so we grabbed that token, and now this packet gets to pass. So usually our result is that we pass. But then we have violating. You have violated the SLA. We don't have any tokens available, and so at this point, we're usually going to drop this traffic. However, if we use multi-rate and multi-color scenarios, then we can actually have a third option available, which is the concept of exceeding. We might allow traffic to burst a little bit more than usual, but we're going to call that exceeding traffic. And once it's been exceeded, we might do something to it other than passing or dropping. For example, we might pass it, but remark the traffic, increase the probability of it getting dropped later on in the network. So when we consider policing from the service provider perspective, this is a great methodology. We can drop all of the traffic that we need that customers are sending us that they shouldn't have sent us. However, what about from the customer perspective? Am I okay with the fact that I'm sending traffic upstream and it's getting dropped? Remember, the biggest thing that we care about in the QoS world is control. And if we're sending our traffic upstream and we're letting the service provider drop it, then we have absolutely no control over the traffic that's getting dropped. They might drop all of our voice traffic and allow all of our internet traffic through. For all we know, that's exactly what's going to happen. We have to assume the worst when we send it upstream to the policer. As such, our goal should be to never allow a policer to drop a packet. If we're sending upstream to our service provider, we want to decide ourselves which traffic gets dropped. In order to allow us to do that, this is where the concept of shaping comes into play. Shaping is going to return that control to us and give us the ability to drop the traffic before we send it upstream, meaning that the policer never drops a packet. Exactly what we want. We're going to buffer our packets as best as we can. That's the Q methodology, right? Congestion management and such. But then at some point we hit that congestion avoidance notion where we're dropping packets and we have to drop those packets. But the way we do this is we leverage the same tool that the policer uses. We're going to use a token bucket methodology to figure out on an interface when we're going to exceed the upstream policer. So if we're ready to send a packet out and we don't have enough tokens in the bucket, we are not going to be able to send that packet. We're going to have to wait for more tokens to show up in the bucket before we can send that packet. We're going to rely once again on that weighted random early detect. So as the queues fill up, because we're not sending traffic now, we're choosing, our scheduler's choosing not to send the traffic that it otherwise could based on this token bucket. So now we're going to rely on red a lot more because we're going to be dropping more traffic. If it was a gig link and now we can only send 10 meg of traffic, well, then we're going to be dropping more traffic than we otherwise would have been. And so just like policing is an ingress concept, shaping is primarily an egress concept. We want to shape the traffic that we're sending upstream once again towards a policer. If there's no policer upstream, then there's really no reason for us to shape our traffic. But again, in order to maintain control of the packets that are getting dropped, we will shape our traffic down as best we can, and when packets do need to be dropped, hey, at least that decision is made by us and not by the upstream service provider. So, as you can imagine, we have a few takeaways from this conversation, the first of which is regarding policing. Policing is going to be used on ingress interfaces where there is a service level agreement. It's going to drop any packets that violate the SLA. Second of all, we have shaping. Shaping is going to be used on our egress interfaces, facing a service provider, facing an interface that is going to use a policer. We do not want to let the policer drop the traffic. We want to maintain control over that and decide which traffic to drop. Lastly, both policing and shaping will rely on this token bucket algorithm. The token bucket is kind of our way of evaluating whether you've exceeded that SLA. And we're going to use a token per bit that we send, and if we have the tokens available, then we can send it. If we don't have the tokens available, then we're going to have to drop that packet. I hope this has been informative for you and I'd like to thank you for viewing. When we're doing our network designs, we want to make sure that we have our QoS policy defined such that it can stretch from one end of the network to the other. We want an end-to-end QoS policy. That's what this blueprint exam objective is all about, after all. However, there are some challenges that are going to impede us from accomplishing this. It's not as simple as simply pulling up an interface and saying, all right, here's my QoS policy, and click and it's done. And in the traditional networking sense, we're going to have to go around to every one of our devices, and not all devices are created the same. So in this video, we're going to explore what some of those challenges might be to deploying an end-to-end QoS policy. Let's take a look. QoS behaves differently on different platforms. For example, let's consider routers versus switches. When we consider how routers are architected, we're going to find that routers are very reliant on their software. They don't have as many ASICs built into them as switches do, which are built for performance. Because we're software driven, we can configure things in a custom fashion, such as, for example, the number of queues on an interface. In the last really series of videos, we've talked about how many queues we can deploy onto some of our interfaces on a router, and it sounds incredible when we think about 16 or 256 or even 4,096 queues. That's because we can carve up those interfaces into however many queues we want using the software methodology. This is also where we're going to be able to perform traffic shaping. Traffic shaping takes some extra features that we don't necessarily have built into hardware, which again is what switches are based on. So ultimately what we have as a result is we have a very flexible system on routers. A lot of questions might come up every now and again when you're designing a network these days. I know I did when I was a relatively junior design engineer. I was like, okay, we've got these awesome layer 3 switches. When would we ever use a router over a layer 3 switch? Because both devices can handle layer 3, right? I mean, way back in the day, routers were for layer 3 and switches were for layer 2, but that's just not the case anymore. So why routers? Well, this is why we would want to consider routers. And we especially get a lot of these QoS settings that we need for WAN links. So in a lot of cases, we're going to want to bring our WAN circuits into routers still, even though, yes, a layer 3 switch can handle that as long as the handoff is Ethernet. But at the same time, we need all of those QoS features. And so we might expect to still deploy routers to WAN edges and internet edges because of this. Now, I accidentally skipped ahead there a little bit, but as we have already discussed, a switch is going to be primarily hardware driven. And the reason they're built on hardware is because they're built for performance. We want to be able to handle all of these large bandwidth links, and we want to handle them at line rate. But because of this, because we're building our switches on ASICs, on hardware, and not on software as much, well, that makes us a little bit more rigid. And here's a great example. Oftentimes we talk about the number of queues. Well, we're going to have a set number of queues on a switch. For example, a lot of switches are going to have exactly 4 output queues. And there's nothing we can do to increase that because it's built into the interface hardware. Now, way back in the day, we didn't used to use MQC commands. However, fortunately, Cisco has synced that up between switches and routers. So that's really nice that we have the same configuration commands on a layer 3 switch as we use on the routing platforms. But keep in mind that if you're on older switches, you might see these MLS QoS commands. That stands for multi-layer switching QoS, and that's what we used to do on old like 3750s and 3560s and such. Furthermore, we're not going to be great at shaping on a switch. However, we can do policing. Policing is usually a little bit easier because we don't need as much buffering space. We're truly just running a token bucket and trying to figure out, should we drop this traffic? And so we've got that built into hardware. We don't need CPU and software to tell us how to do that. So as we see here, we've got differences between routers and switches, and we might think, okay, well, that's good. We have 2 different types of devices that we have to interface with one another. But unfortunately, it gets a little bit more complicated because even within families of devices, whether that family is a set of routers or switches, either way, different products within the family can be different. For example, we see Catalyst 3000s. This would be like the 3650s and the 3850s. Those are going to deploy QoS differently than Catalyst 9Ks. And Catalyst 9Ks will deploy QoS very differently from Catalyst 6Ks. The 6Ks had their own complete set of QoS commands and the way it worked, and even depended on the line card that was installed into a Catalyst 6000, how many queues per interface and such. Furthermore, in the data center space, we're going to see the same thing. A Nexus 3K, for example, versus a Nexus 9K. Very, very different underlying architectures. The strange thing about this one is that the underlying hardware architecture is very similar on the Nexus platform, but the way that we configure it can be very different per platform. We're also going to see this on the more legacy Nexus 5Ks and the Nexus 7Ks, where Cisco tried to emulate the Catalyst 6K configuration onto the 7Ks because they envisioned a lot of 6Ks getting replaced by 7Ks. So the way we configure QoS on a 7K can be very complicated relative to some of the other platforms. Now, on top of all this, we have to consider different domains. What do I mean by domains? Well, what I'm talking about here is, for example, we might have a campus environment. That would be our traditional core distribution and access layer switches. And then we also have a data center. And the data center is built on Nexus equipment, while the campus is built on Catalyst equipment and routers and such. When we look at the campus environment, we're going to find traffic that doesn't exist in data center and vice versa. For example, in campus, we might have voice over IP traffic that we're not usually going to send into the data center unless there happens to be a phone in there, but even then, we don't have a whole lot of users inside the data center. Furthermore, in the data center, we're going to have storage traffic, which is bulk traffic, very large traffic, and then we also might have live migration traffic on top of that. But those traffic types, fortunately, shouldn't go into the campus environment, so we have to build QoS policies that take these localized traffic into account. However, at the same time, this is an end-to-end conversation. Because traffic is traversing between the campus and the data center, we need to make sure we have a policy that stretches across and between these two different domains. And for better or worse, it doesn't stop there, because what about our WAN environment? We've got our wide area networking, and this is characterized by usually much lower bandwidth links. And so our QoS policies might look different in the WAN space. Maybe from a percentage perspective, it just doesn't make any sense for us to reserve a certain amount of traffic that made sense in the campus space. And so we need to make sure that as our voice over IP and other traffic traverse the WAN, that we have a policy that stretches appropriately between the campus and WAN domains. Now, some of these can seem like daunting challenges, but fortunately for us, this concept of deploying an end-to-end QoS policy is far from impossible. We simply need to take these challenges into account when we're doing our network designs, so when we come across one of these hurdles, we are fully prepared to clear it. So when we're considering end-to-end QoS policies, we need to keep a few of these things in mind. First of all, routers and switches, they have very different architectures. We need to start with that. But then we can look within a family of products like the Catalyst series, like the Nexus series inside the data center. And we realize that some of the products inside the same families have major differences, if not the underlying architecture, then in how we configure the QoS. And lastly, we need to consider the different domains as well. So we've got data center QoS, we've got campus QoS, we've got WAN QoS. And we need to take the different traffic types into account that belong exclusively to those domains, while also building policy that stretches across those domains for the traffic types that are going to traverse our entire network. I hope this has been informative for you, and I'd like to thank you for viewing. Well, we've made it this far, and now it's finally time to put everything together and to talk about how we deliver QoS designs into our networks. So we're going to take some of the key concepts that we've talked about in the past, like classification, for example, and shaping and policing and such. And we're going to look at how we want to apply those concepts to our network designs. Let's take a look. Before we go jumping onto equipment and starting to configure quality of service, we need to make sure that we start by defining what that QoS policy is going to be. For example, we need to understand what our traffic classification is going to look like. What this is going to accomplish is we're going to group together similar types of traffic, and more or less we're forming our queues at this point. A traffic class should equate to a queue on an interface. But then we also have to decide what tags are we going to use on these classifications. Our voice should probably get DHCP EF, for example, but what other tags will we use to identify the different groups of traffic that we've now defined? Next, we need to decide what congestion management technique we're going to use. That would be the types of queuing in our infrastructure. Now, in the vast majority of cases, this should be class-based weighted fair queuing with low latency queuing, or LLQ. This would especially be in the case that we have voice over IP. If we don't have voice over IP in our infrastructure, which, these days it's pretty common really to have it, but if we don't have it, then we could consider deploying it without the low latency queue, because there's not a lot of traffic that we want to make sure is prioritized over everything else other than voice over IP traffic. And lastly, we need to decide our congestion avoidance technique. So in a lot of cases, again, especially in Cisco devices that support weighted random early detect, that's exactly what we want to deploy. But it goes beyond just selecting weighted random early detect. That's great. But what we really need to do is we need to decide those percentages, as well as the thresholds on an interface. For example, at what percent full of the queue do we want to start dropping a particular traffic class? So those are some decisions that we have to make before, again, we even touch the CLI on a particular Cisco device. Now, as part of our policy, we also need to define what we call the QoS trust boundary. We haven't talked about this yet, and now's as good a time as any because it's an important part of our QoS design, which is to decide which devices in our network are trustworthy. In other words, I want to trust the tag that they send me, and which devices are not trustworthy. And fortunately, this should be a fairly straightforward conversation. In a network, we're going to want to trust all of the network devices and allow network devices to primarily set our different tags. We don't want to trust necessarily the end devices unless the end device is very specifically allowed to send us QoS tags. So let's look at an example here. If I've got a device hanging off of this switch here on the left, let's just make all of these switches now. And so this device on the left is trying to send a bunch of internet traffic, whatever. I'm uploading files, and because I've downloaded some custom firmware onto my PC, I can set all of my QoS tags to EF. And this is the danger that we have exposed ourselves to, is we want to have this per hop behavior, this differentiated services QoS parameter set, and that's great, except now we have to deliver our specific QoS policy against EF traffic, and yet any device in the network can tag its traffic as EF. And it sounds great to say, let's just trust no tags coming into our edge switches, but unfortunately that doesn't work either, because we have some edge devices like phones that we want to trust. because it's sending the voice over IP calls as EF, and that's exactly what we want on our network. This is where the QoS trust boundary as a configuration set on Cisco devices is really going to come in handy, because we can define all of our interfaces upstream as trusted ports, and then we can define all of our interfaces downstream as not trusted. Furthermore, we can use specific Cisco VoIP commands in order to identify the fact that we have a phone out of particular interface. And at this point, this becomes part of the trusted domain. Now, one thing to be aware of here is that a lot of these Cisco phones have a port attached to them, which allows to connect another PC to them. But fortunately for us, these Cisco phones are going to automatically place that port into the non-trusted domain. So what happens when we get an EF tag coming in from the not trusted domain? Well, simply put, we're going to wipe that tag out. We are not going to trust that anything you send me really is valid from a QoS perspective. Instead, I'm going to tag this packet based on my interface policy. So if you're part of the not trusted domain, then you can expect that your tag is going to be wiped out. So with our QoS trust boundary established, now we need to talk a little bit more about these tags, because we're supposed to figure out which tags to use on which traffic classes. And so we can start to define some of those. For example, we know that best effort traffic, for example, is probably going to use DSCP of 0. That's pretty standard in networks today. And also we know that voice over IP traffic, we can use DSCP EF, that expedited forwarding tag. But this is where things start to get a little bit more nebulous. How exactly do we want to go about classifying the rest of the traffic in our network? Fortunately for us, we get some definition of tags in an RFC. And that RFC specifically is 4594, because it gives us a list of recommended DSCP values for different traffic types. So let's specifically list some of those out. First of all, we have VoIP signaling. VoIP signaling is an important part of voice over IP, but we don't necessarily want to assign EF to it, so we're going to assign CS5. From here, we get into assured forwarding. How do we want to use each AF tag? Well, the recommendation from this RFC is that video conferencing is going to use a tag of AF4, and then that would be 1, 2, or 3, so we'll just call it 4X. Keeping in mind that 4.3 would be the highest drop probability within that range, and 4.1 would be the lowest. From there, they recommend that streaming services be assigned AF3X. Next is low latency. Anything that we would classify as requiring low latency that doesn't fall into a streaming category, that would be AF2X. And lastly, we have high bandwidth flows. Now, high bandwidth flows can be dangerous because they can get in the way of other traffic. And so we don't necessarily want to prioritize these too much. This is why the RFC assigns it as AF1X, but it does allow us to place some higher priority, high bandwidth flows into a traffic class that isn't best effort. Now, these serve as great guidelines, but it's still up to us to look at our network and decide which traffic types on our network fit into which of these categories. Now, there is one other category to discuss, and this is kind of a fun one. It's what we call the scavenger class. Scavenger class sounds pretty ominous, doesn't it? The scavenger class was created because we have a question we might be asking ourselves, which is, okay, it's great that we have this best effort class that's DSCP 0, but what if I need a class that I want to treat worse than best effort? What if my bulk traffic is important because that's work-related, business traffic, but then I think about things like internet traffic that isn't business-related, or potentially entertainment traffic. Maybe we're able to stream TV services across our network. We deliver that to our employees, but we want to classify that as worse than best effort. How do we go about doing that? Well, RFC 4594 gives us a value for this. They tell us to use class selector 1 as our DSCP tag. This traffic type is to be treated the worst of any class in the entire network. And the primary way we're going to enforce that is with our red policies, because we can configure red to give this traffic a 5 or 10% likelihood of being dropped, even if the queue is completely empty. And we can tune that value to whatever we want. But here's the interesting thing. We're using class selector 1. Class selector 1 is technically a higher number than DSCP 0, because class selector 1 is really DSCP of 8. So 8 is greater than 0, and yet 8 is going to be treated worse, less than 0. This is a good reminder to us that these tags are completely arbitrary. We assign a tag to a traffic class, and then we define the policy around that tag and around that traffic class. So it seems odd to say that scavenger has CS1 and best effort is DSCP of 0, which is technically class selector 0, but at the same time it makes sense that we can define a better policy on best effort than we do on the scavenger class. Now lastly, let's look at these topics of shaping and policing. Do we need shaping in our environment? And generally speaking, we are going to want to deploy this into our WAN space at a minimum. But really, here's the answer. Any egress interface in our network that has to follow an upstream SLA should have shaping deployed to it. And the reason for that is because the SLA implies that there's a policer. And remember, we do not want the policer to drop a single packet, because the policer then gets to choose which packet to drop, and I would really rather be the one who gets to decide that, so I can decide not to drop VoIP packets, for example. But what's interesting about this is technically, if I have a 100 meg SLA and I'm on a fast Ethernet link, well then technically I don't need traffic shaping on that at all, because the SLA matches the line rate for that interface. If, however, that's a gig Ethernet interface, well now I run the risk of sending more traffic upstream than what my upstream policer, probably the service provider, is going to allow. And at that point, I absolutely need to configure shaping, again, to give me back that control. So what about policing? In our environments, do we really need policing if we're not a service provider? And generally the answer is no. But again, I'll define it very strictly for us. Any ingress interface where the downstream connection must abide by an SLA. So if we're not a service provider, are we going to have a lot of SLAs in our environment? Probably not. But we might find ourselves in a situation where we do have that. Maybe we have a connection to another organization and we tell the organization they're only allowed to send us so much traffic. At that point, we'd absolutely want to configure a policer on that interface. So fortunately for us, policing and shaping are pretty straightforward. If there's no SLA involved, we generally speaking don't need to worry about either one of those technologies. So this is it. The culmination of all of our quality of service conversations results in this conversation around QoS design. We need to make sure that we start with a policy. It all starts with the policy that we define on a whiteboard or on paper or in a text document. We need to understand that this is the policy that we're going to deploy into our network before we ever touch a CLI. Then we need to establish our QoS trust boundary. We need to know what devices in our network we're trusting. For the most part, that means we're not going to trust any edge devices at all. However, we do need to make sure that we have commands in place to trust IP phones and potentially wireless access points and such. Next, we have our traffic classes decided. We've got our trust boundary established. Now it's time to decide on what tags we're going to use for each traffic class. And fortunately for us, we have RFC 4594 as a guide. We don't have to, strictly speaking, abide by it, but the more we use this standardized approach, not only does it give us a foundation to build our network on, but it also allows it to be more troubleshootable in case Cisco TAC or a consultant is going to come in, or maybe a new hire, and they're going to be working on our network. That gives them a good foundation as well. You know, wouldn't be a lot of fun to troubleshoot a network that's using scavenger class for our voice over IP traffic, for example, even though technically we could make that work. And lastly, shaping and policing. Shaping is always going to be on egress, and we only really need it where we have SLAs that are lower than our line rates. And likewise with policing, always on ingress, but at the same time, we only really need it if we have a downstream SLA. Other than that, we shouldn't see a whole lot of shaping and policing in our infrastructures. I hope this has been informative for you, and I'd like to thank you for viewing. We've reached the end of another skill. That means it's time to review what we've learned by taking a quiz. First up, out of 4 questions, what MQC commands are used to accomplish each of the following functions? While identifying traffic based on the ACL or tag, this is going to be the responsibility of the class map. Next, the policy based on the traffic class. Policies are a key word there, and so this is going to be the policy map. We take a class map and we apply policy to it, and we think about each individual queue and what kinds of policy we could apply, and we think of things like the bandwidth or maybe the queue length, and possibly even making one of those queues a low latency queue. So I would be adding the priority keyword to it. And then lastly, we have service policy. Service policy is going to take a policy map and assign it to an interface. Cisco gives us these 3 different configuration parameters so that we can efficiently and modularly configure our QoS policies. Question 2. What 2 problems can occur if tail drop is used as the congestion avoidance mechanism? Well, the answer here is going to be C and D. TCP global synchronization, that's that mouthful of a problem that we have where we're constantly spiking as far as packet loss is concerned. And so our TCP windows grow and then they all shrink together. And this global synchronization problem can cause major networking issues. And so we use congestion avoidance mechanisms in order to get around that. But the other big problem that we have is this idea of control. If you haven't noticed the theme over the last couple of skills, we like control over which packets are being dropped in our network, and congestion avoidance can give us that control. So C and D again are our answers. Next up, when using the token bucket for policing, what are the 3 possible results for a packet that arrives on the interface? Well, the 3 different results are going to be conforming. That means that, hey, we've got tokens, we can use those tokens in order to send that packet on. And so usually what we do with conforming packets is to pass them. And then we also have violating. These are the 2 most common statuses that we're going to see assigned to packets as they come in. And violating packets, we're going to drop those packets in most cases. However, if we use more advanced token bucket mechanisms, then we can also have this middle ground state, which we call exceeding. Exceeding is typically when we burst traffic, so maybe we've exceeded our allotted bandwidth, but not by that much, and within the parameters that we set forth in the SLA. And so at that point, we could simply give that a pass. We actually have total control over all of the results of these, so pass or drop or what have you. But in a lot of cases with exceeding, we might also consider remarking that traffic. We could take an AF41 packet, for example, and make it AF43. And when we go from 41 to 43, we increase the probability that that packet gets dropped later down the line. Last question. According to RFC 4594, what purpose does the scavenger class serve? We recall that we have this concept of best effort traffic. Best effort traffic is sort of the catch-all, the default for any traffic that we don't explicitly classify. And this is typically going to be assigned the DSCP value of 0. And so the idea here is to give us a class that's treated worse than best effort for things that are completely frivolous in a business environment, like maybe Netflix streaming, I don't know, just as an example, something that we know isn't related to our business. And so, again, we want to prefer the best effort traffic over scavenger class. And the problem is that we can't go lower than 0. We can't go into the negatives, for example. And as a result, what we need is we just need a value that we can assign that tells us to treat this traffic worse. And RFC 4594, this is not a hard and fast set of rules. It's simply recommendations and ways to standardize across different networks. And so if we follow their recommendation, we're going to use class selector 1, that's CS1, a DSCP value of 8, and that is going to be indeed, as we've already answered at this point, treated worse than best effort traffic. Well, that wraps up this quiz. We've covered a lot throughout this skill, so if you feel like you might have missed some key information, then be sure to go back and watch the appropriate videos in order to catch all of that. Otherwise, congratulations on completing Design End-to-End QoS Policy. I hope this has been informative for you. I'd like to thank you for viewing.